K-nearest neighbors just ask the crowd of neighbors. Support vector machines ask a sharper, almost geometric question. If two classes can be separated by a line, which line is the best one? Not just any line that happens to work, the one with the widest possible gap between the classes. That single idea makes support vector machines some of the most powerful classifiers ever built. Back to two features and two classes, blue and amber, and let's say this time they're cleanly separable. We could obviously draw a line between them. And notice, unlike last episode, we're not asking about probabilities anymore. We just want one clean dividing line. The only real question is which line? Because there are infinitely many lines that split these two groups perfectly. This one works, so does this one. And this one? On the training data, they're all flawless, but they are not equally good. Some sit dangerously close to the points and would misjudge the very next example that came along. Here's the support vector machine's answer. Imagine widening each line into a street, pushing the edges out until they just touch the nearest points on either side. The best line is the one whose street is the widest. That width is called the margin, and the SVM picks the line that makes it as large as possible. And here's the elegant part. Only a handful of points actually touch the edges of that street. Those are the support vectors, and they alone define the boundary. You could delete every other point in the dataset, and the line wouldn't budge an inch. The entire model balances on just a few examples. Real data is messier, of course. The classes usually overlap a little, so the SVM allows a few points to slip inside the margin or even onto the wrong side. A setting called C controls how strict it is. A large C fights hard for every single point, while a small c tolerates some mistakes in exchange for a wider, smoother margin. But what if no straight line can separate them at all? Say one class trapped in a ring around the other. This is the SVM's most famous trick. It lifts the points up into a higher dimension where they suddenly can be split by a flat plane. Bring that plane back down and it becomes a curved boundary, a circle. That's the kernel trick, and it lets an SVM draw almost any shape. In Scikit-Learn, the pieces are familiar by now. A standard scalar, then SVC, the support vector classifier, where we choose the kernel and the softness C, then fit, predict, and accuracy score. 2 pages again, let's write it. Here's the program. 2 pages again, every line on screen. Honestly, it looks almost identical to the K-nearest neighbors code from last time, and that's the whole beauty of Scikit-Learn. Let's walk through it. The imports make blobs to generate data, SVC, the support vector classifier, from sklearn.svm standard scalar for scaling, the usual train test split, and accuracy score to grade it. We make 2 blobs again, 200 points, 2 classes, but a bit tighter this time, so they're cleanly separable. That keeps the whole margin idea crisp and easy to see. We split it 80-20 with a fixed random state exactly as before. The test set stays sealed away until the very end, so our final score stays honest. Nothing new here, and that wraps up page 1. Page 2 opens with scaling. Just like K-nearest neighbors, support vector machines care deeply about distances and margins. So we standardize first, fitting the scalar on the training data and transforming both sets. Now the model. We create an SVC and choose the RBF kernel. That's the one that unlocks those curved kernel trick boundaries. And we set C to 1, a nice balanced softness. Then we call fit. This is where it searches for the widest margin boundary and locks in its support vectors. We predict on the test set and score it, about 97% here. We also print how many support vectors it ended up leaning on, usually just a small slice of the data, which is exactly the point of the whole method. A high accuracy resting on only a few support vectors is a good sign. It means the model found a clean, confident boundary. And finally, we plot the two classes colored by their label so we can actually see the groups the SVM has separated. It's the same two blobs from page 1, now drawn out, sitting cleanly apart with that wide street running between them. And that's support vector machines. Find the widest street, balance it on a few support vectors, and bend it with kernels whenever a straight line won't do. Powerful and genuinely elegant. Next time, something completely different and wonderfully easy to read: decision trees.